Okay, so we are talking about the weak base, and I said that a weak base dissociates partially in solution to give BH plus and OH minus, right? That's a general way of writing a weak base. Now, if we say like that, then the equilibrium constant of the base is going to be written as Kb equal to concentration of BH plus times the concentration of OH minus divided by the concentration of BOH at equilibrium. Okay, so if we say like that, therefore Kb should be equal to, of course, Kb is equal to this, and in the same line, you can say Kb times BOH, alright, should be equal to concentration of BH, B plus, and concentration of OH minus. But we know that for any molecule of this that is associated in solution, it gives 1 mole of equal amounts of B plus and OH minus. So which implies that Brett, you say Brett, concentration of OH minus is equal to that of B plus ions in solution. So it means that we can be able to write this same equation as Kb equal to concentration of B plus, or OH minus, all that squared. So in the same light, just like that of the acid, we can say concentration of OH minus is equal to the square root of the Kb, equilibrium constant of the base, times the concentration of the base. Okay, and so the BOH for a weak base can be written as negative log to the base 10 of square root of Kb times concentration of BOH. Okay, and so you follow this formula. So if we are asked to calculate the pH for a weak base, alright, the first thing that you do is you use its Kb that you have been given times the BOH. You are usually given the acid constant, okay, the equilibrium constant of the acid or the base at the exam. So here pH will be given as this. So if you are asked to calculate the pH, the first thing you do is you first of all calculate the pH and then apply pH plus pH equals to 14. Then you make pH the subject of the formula and you calculate the pH. So pH will be equal to 14 minus the pH. Okay. Then this takes us to another relationship. Alright. So hope you have taken note of that formula. This takes us to another relationship. Now, the Ka of an acid, alright, if you take negative log to the base 10 of the equilibrium constant of an acid, we call it the pKa. Okay, so if you hear about the pKa, that will be that. Of course, pKb will be equal to negative log to the base 10 of the Kb. This is for a base, alright. So pK equal to negative log to the base 10 of that, and pKb equal to negative log to the base 10 of that. And of course, just like pH and pOH, pKa plus pKb is equal to 14. Please take note of this because it is very, very important. Now, if you know all of this, alright, let's now talk about how can you talk. Let's now talk about the strength of the acid and the strength of the base. Alright. If you have an acid that is associated, remember Ka is equal to concentration of the H plus times the concentration of the conjugate base divided by the concentration of the acid itself. So if we have increased concentration, if you have an acid which is a stronger acid, it means that more of the molecules are going to dissociate to give H plus and A minus. So it means the concentration of H plus and A minus are going to be increasing solution. So, and the higher the concentration here, the higher the Ka value. And so in other words, the higher the Ka value, the stronger the acid. And now, the higher the Ka value, the smaller the pKa. Alright, so to summarize this for you to understand it, I always write it in this way: that the strength of an acid, alright, is directly proportional to its Ka and inversely proportional to the pKa. Now, if you are given maybe acids in terms of Ka, the one with the higher Ka is going to be the strongest acid, and the one with the highest pKa would rather be the one with the is directly going to be the weakest acid. Okay, so it means that the higher the Ka, the lower the pKa. So please, it's not really a formula, it's just a way for me to make you to understand how acid strength varies with the Ka and the pKa values. Alright, the same thing for a base. The strength of the base will be directly proportional to its Kb. So the higher the Kb, the stronger the base, and the lower the pKb, the stronger the base. Alright, so you see the strength of the base is inversely proportional to the pKb. So the lower the pKb, higher the strength of the acid, and the higher the pKb, the lower the strength of the acid. Okay, so please take a look at it for a second, and here we go. Now let's talk about the ionic dissociation of water. Alright, the ionic dissociation of water. Now at equilibrium, you are going to have at 25 degrees Celsius, or at any time, water can dissociate to give us H plus and OH minus ions. So if you get to write the equilibrium constant of water, Kw, remember for the acid was Ka, for the base was Kb. Now for water is going to be Kw of water is going to be written as concentration of H plus times concentration of OH minus divided by the concentration of water. Now the concentration of water liquid is always considered to be unity. Right, this is liquid, this is aqueous. Now concentration of water in particular is always considered to be unity. Okay. Now if it is unity, it will imply that Kw is going to be equal to concentration of H plus times concentration of OH minus. Simply that way. Alright, simply that way. So Kw is equal to H plus concentration times OH minus concentration, and the value of Kw at 25 degrees Celsius, Kw is equal to 1.0 times 10 to the negative 14 mole squared. Alright, mole squared per dm to the negative 6. Okay, so that is the constant, so that is the value of Ka, and that is why if you take the concentration of or if you take the pH of water at that point, you're going to have a pH of 7, telling you that it is neutral. Okay, now I think that one is very clear, very clear. You can rewind to and pause to copy. Now the next stuff I will just try to throw more light on is how to calculate the pH of water. If you are beginning to calculate the pH of water at any temperature, the problem there is no link between the pH and the temperature. Maybe it can be linked in terms of explanation, but in terms of the formula, there is no connection between the two. So if you know that Kw is equal to concentration of H plus times concentration of OH minus, remember that in water is supposed to give equal amounts of H plus and equal amounts of H plus and OH minus. So you imply that concentration of H plus will be equal to concentration of OH minus. Alright, and so you can be able to write Kw of water as concentration of H plus, all that squared. And if you can be able to write it like this, it means that concentration of H plus in water will be equal to the square root of Kw of water. And if it's that, it implies that the pH of water will give as negative log to the base 10 of its square root of its Kw at any point in time. Alright, so that is that for the acid base equilibrium for that's on the part of water. We have been able to see strong acids, weak acids, although we started with the definitions. We have been able to see strong acids, weak acids, how to calculate their pH values and the relationship between pH and pOH. Okay, now let's move on to titrations. What are we going to say about titration? Because we have seen the equilibrium constant. Now I'll talk to you about the calculation of the pH of a buffer solution when we come to the buffers. That is going to take place immediately after acid-base titrations. Okay, so we are going to end here for this video. Um, in the next video, we continue with titration. We talk about the different types of acid-base titrations, the kind of indicators which you are supposed to use for all of them, and we'll look at the indicators, what are indicators, and why do indicators have color changes. So thank you very much for watching, and see you in the next video.